Welcome to Hypotheses and Justifications. Again, looking at one-way ANOVA. This is the exact same example as in my introduction to one-way ANOVA video. So a university wished to compare the study skills levels of the different years on campus. A researcher randomly selected 10 students entering their first year, 10 students entering their second year, and 10 students entering their third year. The researcher had all of the selected students take a study skills test, which was scored out of 100. The researcher then compared performance by year. The data is recorded below. Can we conclude at the 5% significance level that not all 3 years have the same average performance? So I went through the data in my introduction to one-way ANOVA video, so I'm not going to read them all off this point. We also looked at the box plots in that video. So here are hypotheses. Our ultimate goal is to see if the means are different or not the same. Our null hypothesis will be that the means are the same. So in general, for one-way ANOVA, the null hypothesis is that the means are all the same. So it would basically be like mu1 equals mu2 equals mu3 equals all the way up to however many we have. The alternative hypothesis is simply that they are not all the same. So the means are not all the same. So there's actually a ridiculously long list of different ways this could happen. It could be that mu1 is different and all of the rest are the same. It could be that mu2 is different and all the rest are the same. It could be that all of the means are different from each other. So this one we will not write out in symbols. We're just claiming that the only thing we're claiming is that they are not all identical. From here, we have our specific situation. So in our example, one moment, I need to plug my video. I will be back. Computer's now charging. So for our example, our null hypothesis would essentially be that first year, second year, and third year students all average the same score on the study skills test. So first year, second year, and third year students at the university at the university all average the same score on the study skills exam. And the alternative is simply that the years do not all average the same score. So in either the null hypothesis or the alternative hypothesis, write out explicitly the entire detail. In the other one, you are welcome to eliminate most of the words. So I didn't say first year, second year, and third year students at the university do not all average the same score on the study skills exam. I eliminated a lot of the words because they were just listed in the sentence before. The justification or requirements for one-way ANOVA, there's actually 4 requirements now. We're no longer limited to the 2 that we've seen over and over and over again. So good sampling technique. This is in all samples. So for all of our samples, this is our usual requirements. So we need random and drawn from the entire population. So in our example, we do meet both of these requirements. So this is our usual requirement for any sort of inferential statistics. Now they get a little different. So next up, we need the random samples to be independent. So essentially, what this means is who is picked in one sample doesn't influence who gets picked in another sample. So the individuals picked in a sample has no influence over who gets picked in the other samples. Oops. Okay, so the individuals picked in a sample has no influence over who gets picked in the other samples or for the other samples. So an example of this not being the case might be if, say, you took a sample of third-year students and then chose their younger siblings for other samples, then that has direct influence on who gets picked in the other samples. In this case, in our example, there were just 3 separate random samples, and so they're independent. So in our example, they're just completely random, right? So each was picked randomly and separately. All right, now this third condition is one we're used to seeing. So the population data is normal for each individual population, or we have 2 other ways that we can do this. So the next option, so our or option 2 would be that the samples are size 30 or larger. And option 3, if we don't have the population data, we don't know it's normal, we can look at our sample. As long as our sample is not severely skewed, then we can go ahead and do this. So the sample data, so the samples are somewhat symmetric. not highly skewed. So to do this, our samples were size 10. So in our example, the population data, we don't know if it's normal or not. So we don't know if the population data is normal. We don't know, or the samples are not 30, right? So the samples were size 30. Oh, sorry, 10, size 10, not size 30. So not 30 or larger, which means we have to use option 3. So this was our first year, second year, and third year. If we compare these, none of them are severely skewed. So the tails are not, none of the tails are extremely long compared to the other tails. So no tail or whisker. Is much longer than the whisker on the other side. And so that means the data, none of, trying again. No tail or whisker is much longer than the whisker on the other side. So by that I mean, right, so here's a whisker and a whisker. They're fairly similar in length. Whisker and whisker, fairly similar in length. Whisker and whisker, fairly similar in length. We don't have one side just ridiculously long. And so with that, none of the sample data are particularly skewed. So no sample data is too skewed. So in our example, we do meet the basic requirements. And finally, the very last thing we have is that the populations should have similar variability. So it's rare that we know the population variability. We don't usually know the population standard deviation. So we don't usually know. The population standard deviation. And so instead, what we can do is we'll use the sample standard deviations. And the rule is if we do the largest standard deviation divided by the smallest standard deviation, the rule is that this number should be less than 2. So smaller than 2. So in other words, none of our sample standard deviations is twice the size of one of the other sample standard deviations. Then we take them to be similar enough. So we need to calculate the sample standard deviation for each of our data sets. So if I follow the link to our data in Desmos, oops, we can go ahead and find a standard deviation for the first years, the standard deviation for the second years, and the standard deviation for our third years, right? So we have a standard deviation of 10.5, about 10.0 more or less, and about 11.3. So going back to our notes, for first year, we have S is about 10.5. For second year, S is about 10.0. And for third year, S was about 11.3, I think, if I remember correctly. We can just check that. Yeah, about 11.3. So again, this is our example. So this is from our example. I apologize, my computer is being slow at the moment. Second year had the smallest standard deviations, that would go on the bottom. And third year had the largest. So that would go up top. And so we would be looking at 11.3 divided by 10.0, which is 1.13. Eventually it'll catch up. So 11.3 divided by 10.0, which is 1.13, which is definitely smaller than 2. So in this example, we definitely meet the requirements that our standard deviations are similar. So we've met all four conditions, all four requirements for running a one-way ANOVA test. So in the next video, we will look at calculating what is called the F-score and finding the p-value.